And Tie-Shan Wang is from Lanzhou University in China. And his title is Abnormal Enhancement of Nuclear Reactions in Extreme Environments Studied by Ion Beam Experiments. Dr. Wang.
So, hello, ladies and gentlemen. It's a great opportunity for me to attend the ICCF again. And 25 years ago, I attended the ICCF conference in Hokkaido. And so in 2004, I attended the ICCF in Italy. Now I come back again and meet a lot of old friends, old faces. And I enjoy the presentation very much. But today, I will give a talk about the abnormal enhancement of fusion reaction in different environments studied by ion beam. Once we use the ion beam to study the fusion, that is not cold fusion, it's hot fusion. Then, different from other topic, I will give a talk about our ion beam experiment. Then outline of my talk is introduction, experiment setup, and today I mostly talk about the deuteron-proton lithium reaction and deuteron-proton barium reaction. Okay. Why? Nothing? Huh? 那我看不到。
没电了吗？
不是没电了，网络断了。你那个网络我帮你断的。这就是你断了一下子。他还没，我刚才把它断了。你那有屏幕吗？我这可以看到你的。他那边有。那你给我看一下吧。Okay. Sorry, my screen is dark. I will show another one.
Oh.
Okay. So. Okay.
We see your screen well here.
But on my computer, I can see nothing. What is the reason? I don't know. Someone is shut down. 这个播不了啊。播不了，我只能看。So, I'm sorry for that.
Oh, not at all.
Okay. Yeah. So come back. Yeah. All the nuclear reactions is a beginning of the universal, the proton-to-proton reaction and deuteron tritium reaction and the lithium reaction, so on. But the really situation, the nuclear reaction is between the nucleons, and between the nucleons, it's different from the environment. We know all the reactions in universal, that is a sub-Coulomb-Barry reaction. For example, the DD reaction, the Coulomb-Barry is 519 kiloelectron volt. The cross sections will be changed very rapidly with the decrease of the energy, the projector energy. And the fusion reaction occurred mostly in extremely condition. For example, in solar, this is the plasma situation. The density is 10 to 25. And in nuclear explosion, that is also high density plasma situation. In tokamak, the density is less, but also plasma. The ICF, the laser fusion, is also high density plasma situation. But in laboratory experiment with accelerator, the density is much less and somehow less, but the target is gas, liquid, solid, and high density plasma. And the electromagnetic field situation are also very different. In that case, the reaction will be affected by the environment. When the project bombards the atom as a target, there is electron screen effect. If the environment there are some electromagnetic field, then the Coulomb-Barry will be compressed to thin, even lower. This is so-called the surround screen effect. And what factor can affect the Coulomb barrier? And we know the temperature, density, phase, electromagnetic field. Now, how those factors affect the Coulomb barrier? And in the cold fusion field, we think that is condensed matter, even the lattice confinement fusion and so on. But once we use ion beam to study that, we should think about that is in the temperature is 10 to 7 to 10 to 8 kelvins. Then we use the standard nuclear fusion reaction. The cross sections function is this one, and here we get the gamma factor. The gamma factor affected by the screen energy very much. If that is 0, we can see the gamma factor, this 10 to minus 2,760. If we get a little of the screen, then we will find the gamma factor changes dramatically, many magnitude. Then the penetrations, the probability by the Turner effect increases dramatically. And the previous measurement of the DD reactions in metallic environment has been carried out by different laboratories. This is to show the results from Professor Kasagi in Tohoku University. They have used the palladium oxide, palladium, and the iron, and gold and titanium and so on. They get also this kind of enhancement of the reaction rate. And this data is from the Chersky, Professor Chersky studied many different host material, and they get the screen. Most of them above the 100 electron volt. Below 100 electron volt, that could be understanding by electron screen. And they study this, follow the Z number of the atom. They get some phenomena along the, so when the host material is metallic, then the enhancement factor is much larger. This is the so metallic atom to deuterium ratio, usually close to 1. And if we study the palladium, the proton, deuteron, lithium reaction in different target, we found also big different enhancement of the screen factor. The S factor here, you see the target, different S factor. And about the deuteron lithium 6 and proton lithium 7 reactions, once they got 600 electron volt screen potential, then the enhancement is dramatically very large here. If we see the US, the screen potential, maximum in the palladium lithium, could be 3,719 electron volt. Then the factor is 10 to 88. That is a big factor, and 1 electron volt, kilo electron volt. And even below to 1 kilo electron volt, nobody knows. The ion beam cannot do a lot of things because the cross section is too low. But if we extrapolate this phenomena to the low energy cold fusion region, maybe there's some positive information or some to understanding the mechanism in the low energy could be referred to this kind of trends. And by the observed factor, we see the abnormal enhancement of nuclear reaction in different metallic hosts, the screen energy reported by different group, but the phenomena are very different. The screen effect depends on the hosting material, phase, temperature, density, and so on, other factors. Then we should consider about the charges, the temperature, phase, and coupled constant. By ion beam experiment, we change the phase, charges, state, and temperature, and also the target depth distribution of the target atom. And what we have studied, we use the ion source platform. This is in London University. This one is in the Institute of Modern Physics, Chinese Academy, and this is in Tohoku University. And we study the beam target reaction and measure charged particle products. And here, if you see, this is the original the neutron, proton, lithium reactions spectrometer and the charged particle spectrum. You see clearly, we just measure the charged particle, we know how many reaction years is that. And we study the phase dependence and then change the temperature. Once the lithium target melts, then in the liquid phase, the yield is much higher than the solid phase. This is the phase transformations process, transfer process. And when we change the neutron energy, we use the neutron energy 75 kilo electron volt. The difference is over 10%. When we use the proton energy and the 60 kilo electron volt, the difference between liquid and solid is almost 20%. It's quite larger. It's much larger than the uncertainty. And the phase dependence, we continue to study that, and we will find the previous work and our work, we found the different is several hundreds electron volt. It's the screening factor in liquid lithium target is much larger than that solid target and the gas target. And we study also the liquid lithium target, the temperature dependence, and use the 70 kilo electron volt to project neutron. And then we found just in 100 degree centigrade different, then we found the yields changed somehow. And then we gave the temperature, and then we found the dependence of the temperature. The x-axis is the temperature, and here the screen potential changed, decreased to follow the temperature increment. Then the host dependence, then we change the target situation. This is the pair nuclei reaction, the S factor, and then we use the D2, and then we use the lithium fluorines, and then we use the liquid lithium. Then we obtained the potential for the gas phase. The potential is 240. For the solid phase is 347. For a liquid phase, this already almost 700. This is really very large. By this enhancement, the reaction rate will be changed a lot. And we measure the direct reaction, not only the neutron lithium reaction, we measure also the P0, P1, the two different energy level, and we measure also the alpha reaction. We obtain the potential. Finally, recently we measured the neutron proton barium reaction, and our energy region is the black point here, and this is from the other reference publication. Then we get our potential, and the data is quite different from the different laboratory, but our results show in this region, the urban is so relatively less than others, and also our data agree each other. And by this work, we extract the energy to just to 20 kilo electron volt in this region, and we obtain the potential is larger than the theoretic projection. And by summary, all the reaction rate was enhanced in condensed matter due to the surrounding charges, maybe not. Enhancement in metallic target are always large due to the more spring source from the charges. The report volume disagree with each other from the different laboratories. This is a challenge for us because the experimental environment is quite different and from different laboratories are very different. The enhancement depends on the multi-condition of the host, phase, temperature, and also density. In future, we would like to study the neutron beam, tri-beam experiment, use the neutron beam to bombard the deuterium target. Then we make an interference with the electron beam and the laser beam. Because the electron beam and the laser beam are pulse beam, they can change the reaction environment. We use a constant neutron beam and get the reaction. And if there's some influence from the laser beam and the electron beam, we can find the mechanism. And the second one, we would like to use the neutron beam and the deuterium molecule beam and the tri-deuterium atom beam, then to bombard the target. This is a kind of cluster effect. If there are some difference, this cluster effect will be understood. And another one, we use extremely intensive laser beam. This is for the ICCF. We bombarded the deuterium target. We studied the plasma density distribution and temperature dependence. By this way, we can find the low energy, extremely low energy fusion reaction mechanism. And I hope this information could be helpful for understanding the cold fusion in condensed matter. So this is my talk. Thank you very much.
Thank you very much, too. Very nice talk. We have a question from Dr. Graham Hoopler. So, Graham, please. Sorry, Graham, did you have a question? We might not, we show your mic is muted. So if you could please unmute. Yes, great, thank you.
Is that unmuted now?
Yes, we hear you now.
Oh, okay. Hello, Tie-Shan. Nice talk.
Yes, thank you.
Do you know if Chersky or Kasagi has ever done these experiments with a neutral or negative ion beam?
So actually, Professor Kasagi is one of my co-workers. I noticed that in the front. We discussed about our former results, and neutral beam, it's difficult to use for the ion beam experiment because we need to focus that, extract that, focus that, and also analyze that. Then we need the charge. We have to use the ion beam. Neutral beam is difficult to use.
Or negative ion beam. And the reason I ask
negative ion beam is possible to use, but up to now, I don't think anyone from us have used a negative ion beam.
Okay, the reason I ask is that when a positive ion beam strikes a conductor, an electron jumps from the conductor to the ion before it hits. And that excitation possibly could set up a plasma, or electrons could be attracted to the place where the ion hits and increase the electron density
Yes.
from that effect. So that's why I thought it'd be very useful if one could ever do this with a neutral or negative ion beam.
Yes, but no, because we use the metallic target. The metal is conductive material, and the ion beam is very weak. And in that case, your consideration may be so ignored. because the beam is just the macro ampere level, and the conductivity of the target is very high. And when we use the lithium target, we assume the lithium target is a kind of quasi-plasma, and the lithium is ionic and also some free electron. And in the liquid phase, then the free electron and the positive lithium ion will move inside. In that case, the electromagnetic field could be different from the solid state. This is our understanding for the situation. I don't think that is meaningful by use the negative ion or neutron at all.
Okay.
This is just my opinion. So,
We had one question from Dr. Luciano Ferrari, but is a very brief question because we're a little behind time. So,
oh, sorry for that.
but please go ahead.
Please.
If you have a very quick question, otherwise, I'd encourage you to ask it by email after the session.
Yeah.
Okay. Yes. Well, very good. Thank you very much, Dr. Wang. Very interesting talk.
Yeah.
Dr.
Thank you
Wang,
too.
are you considering to check the effect of magnetic field on the host target?
It's very difficult to check because the ion beam, if you apply the magnetic field, then the ion beam will be changed.
Great.